Hello, welcome to another Learning Glass session. Today we'll talk about isentropic processes, but this time the specific heat is not going to be constant. So isentropic meaning no entropy change from in the process going from one state to another state, and we'll account for the dependence of specific heat on temperature. So Cp as a function of temperature, Cv as a function of temperature. Okay? So isentropic processes, this is entropy does not change. So there's many ways to talk about entropy, but one of the fundamental definitions comes from the heat transfer during a process. So you can get some equal sign here instead of these inequalities. If this process is reversible, you can relate it to heat transfer during a process over T. Some infinitesimal change in entropy is related to this incremental amount of heat transfer. If it's reversible, it's equal with this temperature as well. So if we do this, we can use this definition, and which is related to the second law of thermodynamics, and apply it to the first law. So the combined first and second law expression, has this and the plugged in terms of heat. So we said change in internal energy is balanced by some heat transfer and work transfer, and we can replace this to express the heat transfer by this change in the state variable entropy minus the work transfer, which we also relate in terms of change in state variables. So this is the combined first and second law, and all of these are state variables. So state variable, so we can use this even though it may or may not be reversible. This amount does not depend on path. So that's the nice beauty. One of the beautiful things about thermodynamics is that even though this is defined in terms of a reversible process only, as long as you capture only the state variable parts, it will always work for any process once you replace heat transfer here, because it's a state variable. Okay? And because now you don't even have to worry about the heat. As long as you know this endpoints of the state beginning and at the end, you can use this relationship for any process. That's good. So now, as we did previously, you can then use this to get some idea of some change in entropy in terms of state variables. So the way that this is written, you can say that this is a change in entropy you can relate to a change in internal energy. And as we may remember, enthalpy is related to, it's another way of expressing internal energy. And if you do that, you can express the first law in terms of enthalpy, which is convenient in many processes. And you can also write this change in entropy in terms of enthalpy change. So then what we can do is, say, by doing this integration, we can remember two things. That for any process, this change in internal energy can be related to the specific heat CV. This change in enthalpy for any process can be related to specific heat CP. So using those, you can say that the change in entropy from one temperature and pressure to another temperature and pressure is related to this change in internal energy, which depends on temperature. So that is using this specific heat definition. And in terms of enthalpy, same thing. This entropy change at different temperatures and pressures. This time in terms of CP if we're using enthalpy. So what we did was use a combined first and second law, and you express this in terms of enthalpy and internal energy. There's different reasons to use both, either or. Then we can remember that in real life, the specific heat in many cases changes with temperature. The only reason why it does not change is you're making some simplification, or that you're looking at a process where the temperature changes very little. If the temperature changes a lot, you have to account for the change in specific heat with temperature, or you have to simplify it and lose a little bit of accuracy for convenience of computation. And we've done that a lot in class. So if you were to make that assumption, you can say for constant specific heats, you can relate the change in entropy to this integral where you keep the specific heat constant and then do the integral of dt. And oh, there's a t here, sorry. dt. So have the specific heat out and then take the integral of dt over t. That would give you this natural log. So we've used this expression many times. So this is constant specific heats. That's a specific case where you ignore this relationship with temperature, which is convenient. Of course, it's more convenient for computations, and sometimes it might be accurate if the temperature does not change much. Okay? So when we want to account for this change in specific heat, it adds more complexity to the computation. So one way to account for this is to use tables. So in the tables, there's been a new, different formulation where you use some reference. So for changing specific heat, define this convenient reference in terms of CP. So define this reference entropy related to Cp. So we're going to say that this integral from some reference temperature to some temperature you care about is related to this integral here. This is going to be our reference point, which will allow us to tabulate specific heat effect on the process. Okay, so when we do that, we can write this integral here. So in this specific case here, if we're going to do this integral here, we would be able to say that the integral from T1 to T2, accounting for the change in temperature, can be expressed in terms of these references here. So T reference to T2 which we'll define by this new symbol here. Okay, so that's the idea, that we're going to use a table to get these entropies with changing specific heat. Okay, so once we do that, we can say that, let's see here, where should I put this? So when we do that, we can say for some arbitrary process where the temperature and the pressures change, we can relate that to these reference values from the table. So that's the idea here. In general, you can use CV or Cp to relate this entropy change. I guess it depends on this volume or pressure, but for changing specific heat and using a table approach, Cp is what has been defined to give you this new reference entropy in the tables defined in terms of Cp, and you can use, this is how you'd use a table related to this Cp expression to get some change in entropy. So what you're doing is entropy, well, using this expression, is you're separating this into T and P components. Which you can go in the tables to find the temperature. Found in tables. Okay, so that is one thing. Let's do an example of how to apply this. What the idea is, you can use this to find entropy for one state or entropy change for a process, but specifically it's useful when you have an isentropic process because it allows you to connect one state to the other, where if it's isentropic, you can say that this change is zero and then go from there to connect to the other state. Okay, so let's use this in an analysis of an isentropic process. Okay, so let's say we're doing an ideal gas compression. So for an ideal gas isentropic compression, we can draw this on a TS diagram. So with for an ideal gas, if you're saying that this is going to be isentropic, it's going to go from a compression to one pressure to a higher pressure, and by the ideal gas equation, you increase the temperature with increasing pressure. So this would be T1, T2, and so this is the temperature. Let's say that this is, by the ideal gas equation, the pressure looks like this at constant pressure, and the volume looks like that. So the density increases, or this would be the other way around. The density would increase with temperature, but the point is that you're going to change the state at constant entropy. So that's the ideal gas equation, has these isotherms on this plot that looks like something like this, isobars. So what we're going to do is go from a low pressure to a higher pressure, and if we're talking about an isentropic compression, we can use this relationship here, and that will give us that the change in entropy is 0, which we relate to these relative pressures. I mean, this, yeah, so I'll talk ahead of myself here, but this entropy in the reference framework, we can relate this to this reference enthalpy if the specific heat is changing. And so going from this expression, okay, so solving for this, just working from this equation, what we'll get okay, now so what this is doing here is by using this definition here, we said it's isentropic. That allows us to get this expression. And what we're doing is connecting the pressure change, the change in the pressure from P2 to P1 with a changing specific heat. And we said that the table can help us with this, because the whole idea of using this reference is you can use a table instead of doing this computation. And so to go take a step further from this table is to realize here that to add another parameter to this table approach. So if we were to write this equation again by separating out these two using algebra, to say that you can also write this equation So that gives us a new definition, that this expression here related to this reference entropy for changing specific heat gives rise to this so-called relative pressure. So this is so this PR that we just defined is given by this expression here. It's called relative pressure because it's related to this pressure ratio, and it's not physical because it's this exponent here, but it's used in the context of constant entropy. So it's most useful for isentropic pressure, isentropic processes. To relate two states so that's what it's defined as, some convenient tabulated value which can relate two states with a constant, a changing specific heat for an isentropic. So if you have a constant specific heat, you don't need that, you just need the states. But if this specific, you want to account for this change in specific heat, you have to somehow relate these states to each other. You might need some, if you don't have the information, you can use tables. You can use this integral always, of course, but if you don't have this integral with the specific heat with temperature function, or you don't know the endpoints or the something you need to solve that integral, you can use this approach here, which is tables. Okay, so that is how this relative pressure is defined. So you can also use that in terms of volume. So similarly, you can use the ideal gas to say that this is all for ideal gas, of course. The relative pressure, we can use ideal gas laws to show how this can also be used to define this so-called relative volume. So for delta S equals 0, delta S equals 0, write this bigger. So in the specific case where delta S equals 0, you can use this relative concept. Okay, which we can define this in terms of volume by using this definition. Okay, so now we have these relative pressure and relative volume, which we can use for an ideal gas, for an isentropic process, to account for this change in specific heat to connect one state to the final state after an isentropic process and accounting for this temperature dependence of specific heat. Okay, so the idea is to use these to use tables to connect one state to the other state and account for the change in specific heat. Otherwise, you would have to do this integration, which you may not be able to do when you don't know the endpoints of the integral. So, this relative pressure and relative volume they're found in tables, ideal gas tables to be specific. They're used to relate two different states, T2, P2, V2, So the whole point of this is to account for this change in Cp and Cv with temperature. That's what we're doing here. Okay, so now let's see how this works a little bit. So, if we're going to have an isentropic compression of an ideal gas, keeping into account this variable specific heat, we would write the first law and then try to relate one state to the other. So we're going to apply this to a compression process where the ideal gas changes from a lower pressure to a higher pressure in an isentropic. So isentropic compression, apply the first law, which in this case would be so for a closed system with no chemical reaction, we use enthalpy. Not enthalpy, use internal energy U in the first law. That's why we're writing for a closed isentropic compression, no chemical reaction. This is the best, most convenient way to write the first law of thermodynamics because this extra PV term does not come into play so we can find the work and the heat transfer in terms of internal energy. There might be some PV change which we can relate to work, but it's not going to be due to chemical reaction or flow coming in and out. It's going to be related to the action on the ideal gas. So that's why we need to separate that out, the PV term from the internal energy. So we're not using enthalpy. Okay, so if this is isentropic, then there's no heat transfer as the definition of from the definition of entropy. So that would give us internal energy is balanced with this work transfer, and we can potentially use specific heat to find the change in internal energy, and we can maybe use the ideal gas equation to find this work transfer to solve the problem. Okay, but in this case, if you are given all that you're given is that T1 equals 290 Kelvin and that V2 equals 8 times V1. So when you compress this gas, it's going to become a smaller, or expansion, sorry, it's expansion. Isotropic expansion, where we're going from a more V2. Oh no, this is expansion. You're going to go to a higher volume. So this is the only thing you know. So we know if we were to do this integral, we know that it's going from V2 to V1, but we don't know what the pressure relationship is between there. We can use the ideal gas equation, but we only know T1. We don't know the temperature at the end. And for this integral of CV dt, we don't know the final temperature. Okay, so one thing that we used in the past was this isentropic relationship, which is called isentropic relationship, but we should also remember there's a big assumption for this, is that the big assumption here is that you have constant Cp and Cv to get this expression. So we cannot use this because we want to account for this change in specific heat. We cannot relate T1 to T2. We know the volume change, but we cannot use this isentropic relationship because a big assumption was that you had a constant Cp and Cv. So we have to use something different. What we'll use is this concept of this relative pressures and relative volume so that we can account for the changing specific heat. Okay, so we're going to use and this is table A22, the ideal gas air table. So how do we do that? We're going to use the table. So what we say is that at T1, from the table, that is going to say that the internal energy there is 206.91 and the relative volume there so there's no units. It's going to help us connect one state to the other. So then now that we know, we use the table. This is table A22. We can get this properties of the ideal gas, and we're going to use this relative volume. How we're going to use that? Well, we're going to say, okay, for this given condition at state 1, we know the volume change, and then we also know that we can use the relative volume to help us along, and we're given that this volume change is 8. Oh, this is the other way around, sorry about that. This is the compression. So this is V1, it gets compressed 8 times. So this is 1 over 8. This is given. It gets compressed, starting from 8 to 1. And so that allows us to find the relative volume at the end. Because why? Because it's isentropic. We're using this ratio because it's isentropic process here. So we set this equal to 0. Going from there, we can define these relative pressures and relative volumes from the table. So we found this from the table, and that allows us to find VR2 equals so that's VRT2. Then from the table, that gives us that. That's how we find T2. So we didn't do this integral directly. We used the isentropic assumption to relate these relative volumes. And then once we knew the relative volume at the end, we can link that to the final state, which is given by the table. So that's how we found it. So that's good. So we didn't integrate. We looked this up in the table by using this formulation of the relative pressures. Okay, so then we can find the final volume. For an ideal gas, we can write that. And oh, well, we're given pressure too. P1 equals so given that, we knew that, and now we know this ratio of temperatures this is 1 over 8 or 8. So P2 equals 1800 kPa. That's good. And then we also know the internal energy change, so we can relate that to the work. We literally just pull this from the table. So this is work in because it's negative. Okay, so that's how we would do this analysis if we wanted to account for the change in specific heat. We can no longer use this isentropic relationship that we've called isentropic, but there's actually two assumptions in this. It's isentropic constant heat capacity. That's the assumption that you need to get this expression, which we've used many times, and we're going to use again in this for a lot of our processes. But if you wanted to account for this temperature dependence of the specific heat, you can do these integrals, but you would have to you need more information to be able to do this integration. And another way to do this is to use, for isentropic relationships, this concept of relative pressures and relative volumes, which are in tables. So what we did for this example is saying, knowing this starting temperature and knowing the change in the volume, you can find the relative volume at the end. If it's isentropic, that will lead you to a different state. That's how you connected these two. We're saying that for an isentropic process, you can find this relative volume at the end, and that's your link to the state at the end. And then you can go from there. So this is the way to use the tables to find this isentropic process analysis accounting for this temperature dependence. Okay, so that is it. I'll see you guys next time. Yes.